Yay, I've got the recording on properly this time. Woohoo, it's a big day for Mr. Younger, everybody. All right, first off, I want to let you know, Dr. Wright, I didn't realize, I thought most of y'all had either Mr. Greer or Mr. Ippolito, but Dr. Wright was telling me that most of y'all came from his class, and he wanted to tell you all hi, and they hope y'all are doing well, and he even said nice things about me to tell y'all, but I figure I'll let y'all develop your own opinion about me. So anyways, I had talked to him last night, and he's sorry he couldn't teach you again. Him and his wife decided that he was going to go ahead and retire, so he's not here this semester. But you know how he is; he's a hardworking man, so he's been working probably just as much as he was when he worked as a department head since he's actually retired. Because lo and behold, 7 people retired, or 6 out of 7 people retired in this last 3 semesters, and 5 of them retired just this past semester, and that left only me as the only faculty member. And we've had to deal with the COVID stuff. We had to make all new labs, and Dr. Wright and I have been working together, but he's probably run circles around me. So I just want to let you guys know he's still around. He's emeritus now. And like I said, he's probably working harder than ever, but he hopes to be able to go on a mission with his wife soon. But I think he's probably going to take about a year before he does that. So anyways, anybody have any questions before we start our class? No one has any questions, really? So the homeworks, I didn't have them done at the beginning of class last time, but I finished them that night on the 13th. So they've been up uh, for some time, but you might not have seen them. Remember, every week especially when we start a new chapter, but every week there's always a homework assignment that's due on the following Monday at 9:30 a.m. So this week's particularly onerous because we've got a chapter 19 that was covered, as well as we finished up chapter 18, and then today we're doing chapter 20, and then Friday we're doing chapter 23. So there's literally 4 different sets of homework, and actually one of them's broken up into 2 sets. So there's a lot of homework that's going to be due Monday, but I think I'm probably, out of fairness, I'm probably going to make the chapter 23 due on Wednesday as opposed to Monday. Right now it's listed as Monday, so you guys definitely need to start it. I wanted to let you know that, as I told you before, when I cover a chapter, I cover the sections that are listed in the syllabus, but the homeworks and even the practice tests are based on the entirety of the chapter. So you still got to pretty much read the rest of the chapter. But what I've done with the homeworks, I've tried to take the sections that are not relevant to the parts that I actually covered, and either made those left them as full points if they were tutorial type questions or coaching questions, because those are ones where they're actually teaching the material in addition to what you've got gleaned from from reading the text. So I've left those at full value, which is basically, I give you the number of points that the average student takes. So if a problem's worth 7 points in your homework system, that means that nationwide, the average student took 7 minutes to complete it. So if you're taking 14, 15 minutes, probably you're not getting something. You need to go back, try read again, sort of that sort of thing. But also, if it had other questions that were from those sections that we didn't really cover, I tried to either completely erase them from the homework, or I just made them extra credit. Okay, so you don't need to feel obligated to do any of the extra credit points. If you want extra credit points, then by all means try them, but really just limit yourself to the ones that are regular credit, and you should be more than prepared. I also sent out an email yesterday about the practice tests. It's got a lot of weird symbols and stuff in it. I've sent you a sort of a key, if you will, to being able to understand what those things are. Okay, the focus is not that great. I sent you a key to being able to understand what those things are. So in a lot of cases, what you're seeing is the browser or Canvas, one of the two, is having a hard time interpreting, and it should be mostly in the answers, but it's having a hard time interpreting what the answers mean, because it'll say like 1.66 ampersand $ 47 or something weird like that. So what I sent you was basically a key to understanding those. In most cases, it's just like there's a special symbol for multiplication that's not just X, and that's what the one is that usually comes after like the 1.66. It ends in a semicolon, by the way. The one that starts off is SUP, S-U-P. It's got a less than symbol, S-U-P, greater than symbol. That means begin the subscript. So when you put that on one side, everything that comes after it's going to be subscripted or superscripted, i.e. an exponent, until you get to the next one where it says less than slash sup greater than, in which case that means in subscript or superscript, excuse me. And then there's another one for the Greek letter mu. So that should clear it all up. Have y'all ran into any practice test questions that actually had text in the actual question that had weird symbols in it instead of just the ones in the answers? So far, I only saw ones in the answers. Has anyone tried I know a couple people have tried the practice test. Oh, just the answers I got from Kyle. Good deal. Okay. That's what I thought it was. I was afraid maybe different browsers might be interpreting it differently, in which case y'all be having problems even with the questions. So, all right. Yes.
Is the actual test going to have those like sub, soup, and stuff like that?
No, because it's only going to have like 5 questions. I would be pretty bad instructor if I don't take the time to fix those. It's not hard to fix, one question, but it's really a pain when you're trying to fix, in that case, several hundred. Like I said, it took me on the order of an hour to fix 10 of them. So, but I'll definitely make sure it's cleaner than that on the actual test.
Okay, and it's not physics related, but today's my birthday.
Happy birthday. Awesome.
Thank you.
Are you what, like 20 now or something?
21.
21. Uh-oh. I'm assuming you're going out to have a nice Coca-Cola this afternoon.
Yes, indeed.
Well, happy birthday. That's awesome.
Thank you.
I have a question.
All right. So we got to start off. Oh, I don't know. I always hit that button. God, I'm like an old person up here. Wow, my sciatica. Okay. We got to start talking about chapter 20.
I have a question.
You can hardly hear her, but someone's saying she has a question.
Oh, thank you. Who was that? Elizabeth?
Rihanna.
Who had the question?
Rihanna.
Oh, Rihanna, I see. Okay. Yes, Rihanna, how can I help you?
So I know you posted the practice test, but is that something just for our practice, or we have to turn that in for a grade?
No, it's completely non-graded. I mean, it'll show up in the grade book, and until I fix it, it'll even use it in calculating your grade. But I have to each time go back and fix it to make sure it's not. It will not affect your grade negatively in any way. I explained to students last time, the practice test is me giving you a chance to see what the test will actually look like. And at the end of the semester, if it looks like you're maybe a point shy of an A or something like that, and I look and I see you've been taking a lot of practice tests, then I'm probably going to give you that point. That's about it. All it'll ever be used for. It'll never be used for anything negative, but only something positive.
Okay, thank you.
Just as a rule of thumb, and I'm not picking on Rihanna by any stretch of the imagination. This is a very common thing that happens to my students in college, so I got to let them know. In high school, it's very much the norm for teachers to make practice tests. In college, it is very much, especially at the university level, it's very much frowned upon. Normally, the people that take the time to make them are looked at suspiciously, like they're not doing a good job teaching, so they're actually just making this practice test to make themselves feel better about the crappy job they're doing. And sometimes they even make them in such a way that maybe they're literally giving you the exact questions from the test. And then, of course, department heads and other faculty members really hate that faculty member then, because they're really just trying to make this pool where all the students take their class, because it's an easy class where you're literally given the test questions before the test. So the short end of the short part of the story, or the short way of explaining it, is basically saying whenever a college or a university instructor takes the time to give you a practice test, it is highly, 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 highly recommended you take it. It's almost always going to be something that will bite you in the rear if you do not. I have a different philosophy than those, and I am very much of the university model, like the German system, where the college and university is not a place to teach. It's actually a place to create new knowledge. That I actually believe that myself. That being said, I'm teaching at a community college for a reason, and the reason is that I like the teaching aspect of college. So my philosophy on this practice test thing is, if as long as you're giving, 10 or more questions for every one test question that actually appears on your test, then you're fully justified, because what you're doing is you're sort of doing what they did in the 1950s and 60s, when the space race and the nuclear arms race and all that stuff started. People were dying to get into physics and chemistry and engineering. And if you talk to a typical student in college at that time, they are trying to get into the physics program, or they're trying to get into the chemistry or the engineering program. Basically, what you find them doing is doing every physics problem they could find, or every chemistry problem they could find, or every engineering problem they could find, so they could learn as much as possible. And then, lo and behold, the test would come out of that. So that's my philosophy. That's why I give you basically a practice test made out of the bank of questions that I usually use for the actual test. So if you took it, an infinite number of times, you absolutely would have seen every question that will be on my test. But I give the extra little caveat that 10% of the points can come from something not put in there, but I haven't ever used that 10% yet. So anyway, so just a rule of thumb, folks. One, your syllabus is the contract between you and your instructor. Always take that seriously. Know that like the back of your hand. It is your contract that dictates what the instructor can and cannot do. And if an instructor is not doing things according to that, then, and your grade comes out the way you don't like it, then you basically can take that up with the dean. After, of course, you address it with the instructor. You can take that up with the dean, and you will win if the instructor didn't obey his own syllabus, his or her own syllabus. The other rule is, if an instructor in college or at a university ever gives you a practice test, always, always, always do that. Okay. So that's my little soapbox. I'll get off of it now. Yes.
See, our test is Friday though.
Yes, sir. It'll open up on Friday, and I'm definitely giving you till Monday, but I'll probably give you till Wednesday to get it done.
Okay. Thank you.
Okay. Sometimes I used to give students multiple attempts. I haven't decided yet on this one. I might do that. I might give you maybe 3 attempts, and I'll take only your highest score. Okay. But I will let y'all know when that actually opens up, what the rule is and that sort of thing. All right. So let's talk about magnetism. So you've probably all experienced magnets before. And basically, originally in the Stone Age, it was discovered that certain stones would literally attract other stones, like they sort of stuck together in some sense, other than like a sticky thing, just literally 2 metals sticking together. And they were called lodestones. In Latin, that would have been ferrum, for what ultimately became known as iron. That's why iron has the symbol Fe in the periodic table. It turns out there's 3 types of materials that are magnetic. One is ferromagnetic, which means it's like iron, obviously, because it starts off with a ferro. But what that means is not only is it magnetic, but it tends to stay magnetic over a long period of time. Then there's these elements, or these things called paramagnetic. And basically, if you expose one of these materials to a strong magnetic field, it'll then become magnetic. And you can, for instance, stick something against it while it's in that magnetic field, and something will stick to it. That is a paramagnetic material. But as soon as you take that material out of the magnetic field, it loses its magnetism. Okay. Then there's a third thing called diamagnetic, and diamagnetic is really weird in that it's not magnetic normally. If you submerge it in a magnetic field, then it will develop a magnetic field, but oddly enough, it'll develop a magnetic field that points in the opposite direction as the magnetic field it's in. So normally, you know, a magnetic field in a metal or something would line up with the magnetic field that it's immersed in. In this case, it actually would do the opposite. But again, just like paramagnetic, once you pull it out of the field, it would disappear. So those are the three types of materials. Well, it turns out, as best we can tell, what happens with those materials when they're immersed in a magnetic field is basically there's large regions where several molecules or atoms, depending on what kind of material it is, several molecules or atoms all group together and align their magnetic fields in the same way. Neighborhoods of atoms and stuff like that, domains is what they're really called. But large chunks of them do that. And then other parts, the individual atoms and molecules don't necessarily align like the domains do. But by and large, there's a big chunk of domains in the atom, or excuse me, in the solid that actually develops this magnetic field. I shouldn't say solid because we actually have them in liquids as well. But those regions, those domains, if they stay after the magnetic field is removed, then that's a ferromagnetic material. If they just disperse after the magnetic field is removed, then it's either or paramagnetic. But that's what we think is actually causing them, as best we can tell. And the reason why individual atoms or molecules might actually have magnetic fields to them is it turns out there's, just like we talked about the electric dipole, there's something called a magnetic dipole that exists. And you can make one anytime you have a current going around in a circle, okay? And a current, remember we learned last time, current is a certain amount of charge moving through a point in space in a certain amount of time. If you divide the total charge by the point in space, I mean by the time, you'll get the actual current. Well, whenever you have a electron, for instance, going around in a circle, that creates a magnetic field sticking out of the center, either going down, depending on which way it's rotating, or going up. In fact, if the electron's going around this way, then the magnetic field sticks down. If the electron is going around this way, then the magnetic field sticks up. That's called a magnetic dipole, and that's what atoms and molecules can sort of form. And that's why we believe the individual molecules and or atoms can actually have a magnetic field. And then when you submerge them, the whole material in a magnetic field, all of those individual atoms that have their electrons, you know, orbiting every which way, all of a sudden a large group of them get together where all their little magnetic fields are all aligned. That's one of the domains. Okay. Not only that, you can see that if you look at that mechanical model, if you actually struck that metal while it was in that magnetic field, you might even jostle up a few more to make the regions, the domains bigger. And also, after you take it out of the magnetic field, say it's a ferromagnetic material, if you go and hit stuff with it really hard, you could actually break up the domains a little bit. Or if you subject it to heat, you'd also get the idea, because that makes them vibrate a little bit more fast and moving a little more fast quickly, so that the parts are separated and so much stuff like that would ultimately cause those domains to hold on to each other within it more weakly. And then if you hit it, you'd even have a better chance of demagnetizing it. So just by that model, you can make some pretty robust conclusions about how magnets should behave and stuff like that. So that gives us a little intro to how magnetic materials exist. You've all seen probably bar magnets and horseshoe magnets. You know, horseshoe magnet shaped like a horseshoe, literally, and one end will be the North Pole and the other end will be the South Pole. Bar magnets are the same way, except instead of being a curve, one end's the North Pole, one end's the South Pole. But they have this neat property that if you cut that bar magnet in half, it doesn't leave you with a South Pole and a North Pole. It actually leaves you with a north-south and a south or north-south again. So it turns out in all our studies, we never once found an isolated north pole of a magnet, nor an isolated south pole of a magnet. That would be called a magnetic monopole as opposed to a dipole. And we've never found those. And we don't believe they exist. And Maxwell's equations are consistent with them not existing. Maxwell's equations are the four equations that James Clerk Maxwell discovered on his own after studying all the robust experimental evidence that had been gained by Faraday and Oersted and all these other people at the time, and he put them together in a vector calculus form that was just beautiful, and even solved a couple problems that people had missed. So all of Maxwell's equations also suggest there's no such thing as a magnetic dipole, or excuse me, magnetic monopole. So that gives you the introduction to it. So just remember that basically when you cut a magnet in half, it's going to make in two north-south poles on one half, and a north-south pole on one half, and then another north-south pole on the other half. You're never going to just cut it in half and leave the north and the south. If you look at iron filings, so if you take a piece of plexiglass and lay a bar magnet under it, and then dump some iron filings on top of it, this is actually a lab you would normally do in a face-to-face lab. You would actually get these iron filings all lining up along the magnetic field lines, and you get actually a map of the magnetic field lines. So unlike the electric field lines, which is really hard to see directly, but you can see the equal potential lines, the magnetic field lines you can see really readily. It's quite easy. So just like the electric field lines, they are everywhere parallel to the magnetic field, and the closer the lines are together, the stronger the magnetic field is, just like the closer the electric field lines were together, the stronger they were. Now, in the electric field lines, we always had them originating on a positive charge, and if there was a negative charge around, they would actually terminate on the negative charge. But if it was just a single charge, they would go on forever. They'd be continuous lines going on forever, and basically would never just disappear. With the case of a magnet, since you only have north and south always together, then you're always going to have magnetic field lines making closed loops. And here's the rule. So everybody listen to this. This may help you in some problems. Magnetic field lines, now I say this in jest, and I hope I don't offend anyone, but magnetic field lines are like retired people. They leave the north and move into the south. Okay, so how many retired people do you know that retired from Virginia or West Virginia or Pennsylvania and then moved down to Florida? Well, that's what field lines do. They come out of the North Pole and then loop back in and come into the South Pole. Okay, so that's the way the field lines point, and that comes in handy sometimes when you're trying to solve vector problems and stuff like that. So field lines leave the north and enter the south. And when you put two north poles next to each other, they're like poles and they repel just like charges repel. And when you put a north pole next to a south pole, they attract because they're unlike poles, and therefore they attract just like unlike charges. So that's sort of the rules. Let me give you a couple drawings and a couple things that will help you better understand what we're talking about, and then we'll go on into the more mathematical aspects of this chapter. So if you actually had a bar magnet and you put it under a piece of plexiglass, okay, and say this was north and this was south, well, remember the field lines would actually leave from the north and go to the south. Okay, and what would happen is they get a little weaker out here, a little weaker in here, a little weaker in here, and so on and so forth. This one would go way around here like that. So that's what the field lines look like for a horseshoe magnet. There you go. If we did a bar magnet, that's a little easier to understand. So this is the North Pole. That's the South Pole. So the field lines do this. And they continue through the metal. I'm just not showing it, okay? But they are leaving the north and going into the south. And they should be symmetric. I'm not drawing them as symmetrically as they should be drawn, but because it's sort of fairly uniform, you'd expect any field line leaving the same distance from the center line as this one did should be exactly the same shape. But I missed that a little bit. I can do it this way You can do it this way. And even these lines that you see like this, they look like they're going on forever, but they're really not. They're just going so far out and then coming way back in. But that's basically what the field lines look like for a bar magnet. If you actually were to take a compass, let's say we stuck a compass right here, what we would find out is that the magnetic bar in the compass, the north end, would actually point towards the south. So the north end of the compass points this way. In fact, what that means when we think about our Earth, it has this magnetic field. And by the way, you know, a compass doesn't work that well. It's not as good as a North Star and various other things, strictly because the north pole of the Earth is not at the north pole of the Earth. So the north magnetic pole of the Earth is up in Canada, and the lines are doing like this. But here's the neat thing. We know that if we're right here, then the north end of the magnet in the compass points to the north. So guess what? The north pole of the Earth is actually a south pole. And the south pole of the Earth is actually a magnetic north pole. Okay, so that's some information that you'll see you sort of need for the concepts of the course, and just for being an educated person in case you ever appear on Jeopardy or something fun like that. Any questions about that stuff so far? All right, so there's a lot of information there. You'll get that all from the reading, except that your book didn't talk about paramagnetism and diamagnetism. I just gave you that extra. Students have suggested that they would like multiple attempts on the test, and I'm leaning towards that as well. So like I said, I'll keep you guys in mind. The midterm and the final will not be like that at all, though. They're definitely going to be a single shot. Okay. So now the next thing we need to discuss is how do you create a magnetic field other than the ways I told you about submersing a ferromagnetic, paramagnetic, or diamagnetic material into a magnetic field that already existed. Well, it turns out that currents make magnetic fields. And here's the neat thing about it. We used to think in nature there were, I'm going to turn it back to the camera because I like people looking at me when I'm talking to them. Okay. So before we knew about the nucleus inside the atom, we used to think there was a gravity force, a gravitational force, in other words, and there was an electric force, which we, could tell like when we rub fur on a piece of amber, hardened amber, it would attract little pieces of paper or whatever, right? So that was a electric force. We also found these lodestones, and they would make a magnetic force. And then, of course, Newton had discovered the law of gravity, so we knew of a gravitational force. And then later, we discovered there's actually a force inside of the atom, because we discovered that the nucleus of an atom is neutrons and protons. And obviously, neutrons don't have any charge, so they don't care about the protons. But certainly, protons don't want to be next to each other. Yet there's something that's holding a proton right next to a proton, which meant, okay, there's a force, and it has to be stronger than the electric force, or the electric force would blow the nucleus apart. So that became the nuclear force. And then later we discovered that those nuclei would actually break apart sometimes in a certain type of decay. And we discovered that that needed to make another force called the weak nuclear force. So the weak nuclear force is weaker than the nuclear force, and if I remember correctly, it's supposed to be stronger than the electric force, but still weaker than the nuclear force. So there was electric force, magnetic force, gravity, strong force. I'm really having a hard time this being backwards, and the weak nuclear force. So there are 5 forces. Well, when Maxwell put his equations together it was apparently obvious that magnetic and electric forces had a lot in common. And in fact, Einstein ultimately was able to use his theory of relativity to show that the electric force and the magnetic force are in fact the exact same thing. So let me explain how that is, and then you'll see that this is really interesting, because what we think is magnetism turns out to be electricity in another, or electric force in another venue. So what we find out is there's something called the Lorentz force law. And the Lorentz force law says that the force on a charge, and I'm just taking a magnitude here because it turns out it needs a fancy mathematical thing to actually show the direction. That mathematical thing is called a cross product, and it involves a vector equation. It's kind of ugly, but we can deal with it without doing that. So the force on a charge Q is actually proportional to the charge Q. But here's the weird part. It's also proportional to the velocity. So what that means is a magnetic field applies no force to anything without a charge, and it also applies no force to anything charged that's not moving. So something's got to be moving, right? So if you look at a wire, and consider that there's a charge, or excuse me, there's a current I coming out of it that way, then what you know is happening is little electrons are moving every which way, but on average, a good chunk of them are moving this way at a certain speed, and so on and so forth, right? So obviously when this wire is just sitting here, this is going to create forces on the a magnetic field is actually going to cause forces on these individual charges because they're moving. And in fact, what we learn is that this wire carrying a current actually creates a magnetic field, and that magnetic field goes like this. So if I were to grab this wire with my right hand, it's important that you use your right hand. So I could grab it like this. See, this points in the direction of the current, or I could grab it like this, where that's coming out the bottom. But what I want to do is grab it so that my right thumb can point in the direction of the current. When I do that and I look, my fingers actually wrap around the wire in the direction that the magnetic field points. So y'all see that? It's my right hand, the thumb's coming out, the current's coming out. So if I draw that same wire from above, we would mark that the current is coming out by putting a single dot in the middle. It's like you're looking at the front of the tip of an arrow, whereas if it was going in, we'd put an X, so then it's like you're looking at the little feathers on the back of the arrow. So what that means is the magnetic field is concentric, meaning it's centered on the center of the current, and it goes around in a counterclockwise direction. And the farther you are away from the wire, the weaker the magnetic field gets. Okay, so that's the direction of the magnetic field. So we can see that a charge is affected by a magnetic field. Oh, and I forgot this part. Only if it has a charge that's not positive. I mean, that's not zero, a velocity, and then it's in a magnetic field. So if I want to say, here's a charge here, Q, and let's say it's moving at some velocity. Let's say it's just sitting perfectly still. Okay. If it's sitting perfectly still, then we can understand that this magnetic field is not going to make this particle move at all. This is the charge Q, by the way. Okay. But if it's moving with any velocity v, say, then the Lorentz force is going to kick in and cause the magnetic field that's right here. That's going to cause it to experience a force. Now, the direction of the force we'll talk about later. It's a weird thing, but right now it's important just to know that it will cause a force, and the force is going to be felt by this charge Q because it has a velocity v, and it's in the magnetic field B created by the wire. So this is how Einstein showed that the actual electric field, the magnetic field, are one and the same thing. imagine for a second that this charged particle is moving along with the charges. In other words, its velocity is not zero, but its velocity is in fact exactly the velocity of these electrons. If that's the case, then there's no current in this field because I mean in that reference frame, because the charges aren't moving. Without the charges moving, you have no current, but you both have to agree, no matter what field you're in, or what frame you're in, the one where the charge is moving this way or the one where the charge is moving along with the current carrying electrons, in both cases, the charge is going to actually experience a force, and we need to be able to make sure that makes sense. Well, the only way you can do that is say, well, if there's no current, the charge must be experiencing a force due to the electric field. And when Einstein used his contraction formula, basically found that when he moved along with the currents, that would actually cause the positive charges to actually be closer together. So it gave it a net positive charge. And lo and behold, when you do the calculation, you'll get the exact same force you had before in the other frame. So one way of looking at electricity and magnetism is that because of the theory of special relativity, which turns out to be the single most tested theory in the history of mankind and has never once failed, because of that, the electric field and the magnetic field have to both exist. And in fact, one of them is the exact same thing as the other in certain cases. Okay, so that gives you a little bit deeper understanding of why we have a magnetic field and an electric field. The good news is that those are just sort of concepts that's nice to understand. It's not much, well, it's not easy for me to construct questions to ask you stuff about that relativity link. I just wanted you to have some understanding that, hey, if the particle had a velocity v and that velocity happened to match the electron's velocity, then there's no current in that frame. Yet we would still agree in another frame, the frame in which the wire was not sitting still, that the same charge which had a velocity would in fact have a force on it, and those two forces have to be the same. And the only way you can do that is you have to say that there's an electric force in one frame and a magnetic force in the other. All right. So now that we've given you all that intro stuff, I want to tell you about the electric current and how it produces a magnetic field. I've sort of already hinted at it. Basically, when you have a current carrying wire like this one, if you hold your right hand, again, gripping around the current carrying wire, you can do it one of two ways, that way or that way. If you do that in such a way that your thumb points in the same direction as the current, and remember, you got to do it with your right hand. It's going to be really tricky for right-handed people when they're trying to work their problem out writing with their right hand, and they end up doing the math with their left hand, and you'll get everything exactly wrong. Okay, so it's got to be with your right hand. But what we find is that when you actually do that, your fingers coil around the wire in the direction of the magnetic field. Now, the magnetic field is everywhere perpendicular to the actual current. So the current's coming out of the page here, and then perpendicular to that is the magnetic field there. The magnetic field right there is that. The magnetic field right where this arrow is drawn is that way, and the magnetic field where this arrow is drawn is that way. It will, in fact, make concentric circles, and the magnitude of that magnetic field is mu 0, that's a neat new constant, times the current I over 2 pi times the distance away from the center. So if I go out 1 meter, the magnetic field strength might be, and here's the unit, by the way, might be, let's say, 0.001 Tesla. If I then go out 2 meters, it's now going to be 0.0005 Tesla. In other words, if I double the distance, I cut the magnetic field strength in half. If I triple the distance, I cut the magnetic field strength by 1/3. So this don't have the R squared like Coulomb's law did, but it does have a 1/R relationship. As I said, the unit for the magnetic field that we use in the SI system is the Tesla, like the car, but both of which are named after Nikola Tesla, was a very interesting character. He was like 6'5", and I think he weighed like 92 pounds, but he was brilliant. And he walked around with like 6-inch tall cork bottom shoes all the time, because at any point he might be compelled to do a cool physics demonstration, which would require him to possibly risk life and death to deal with millions and millions of volts. So he always kept his insulating shoes on just to give him an extra modicum of protection. But he was friends with, for instance, Samuel Clemens, which you guys know of as, anybody know Samuel Clemens? Huckleberry Finn? Yeah, Mark Twain. He was friends with Mark Twain. So he's the same time period. Also the same time period as Edison, and the same time period of another guy by the name of Westinghouse. And in fact, Westinghouse and Tesla and Edison took turns metaphorically raping Tesla. Basically, I say metaphorically because it was financial. They kept stealing patents from him and stuff like that. This was kind of a sad situation, but that was the big battle of AC/DC, not the group, but the battle of whether we're going to electrify America with alternating current or direct current. And Tesla's the reason that we actually have 60 hertz electricity coming into our house now. That was all from Tesla. So anyways, that's what it is. There's another unit of the electric field called the Gauss. And basically 1 Tesla is equal to 10 to the 4th Gauss. So that's Gauss, and it's normally just written G. So that's another unit of magnetic field strength. Basically a Gauss, the Earth's magnetic field is about a half a Gauss. Typical MRI, which you probably heard of before, it's a magnetic resonance imaging device that you get when you have say a torn ACL or a jacked up shoulder. Like, I had my shoulder completely replaced, and I had to have MRIs and CTs before that. But with that type of device, it's actually called a nuclear magnetic resonance imaging device, but they took off the word nuclear for obvious fear reasons. But anyways, when you get inside of that creates a very, very strong magnetic field, and a typical magnetic field for a MRI is on the order of a Tesla. So maybe, a half a Tesla to 1.5 Teslas. So a Tesla is a really, really big unit of magnetic field strength. It's about 10,000 times the strength of the Earth's magnetic field. And we can do a simple problem. Let's say we have a current carrying wire. Carries a current of 1 amp. Remember, I told you an amp's a big unit too. An amp normally will melt a small wire rather quickly, but 1 amp is, basically 1 coulomb of charge passing through a single point in the circuit every second. And a coulomb of charge is 10 to the 22 electrons, basically. It's carries a current of 1 amp. What is the magnetic field strength at, let's say, 10 centimeters away? At 20 centimeters? And let's say at 30 centimeters. So that's a very typical, easy problem, but it is a typical problem. So I'm going to imagine a wire like so, has a current I equals 1 amp coming out. And I know the magnetic field goes like this. Notice how I drew it in front of the wire there. And this distance from here to here is 10 centimeters. So now I can draw this one be 20 centimeters, and so on and so forth. Okay, so that's the actual problem we're solving. Now you also get to find out what mu zero is. So the magnetic field, this is part A, magnetic field is equal to mu I over 2 pi r. So it turns out mu zero is 4 times pi times 10 to the negative 7th. That's what mu zero is. And the units, because notice you're going to need a Tesla coming out. I got to get rid of a meter in the bottom, and I got to get rid of an amp in the top. So it's got to be a Tesla. Then I got to get rid of that meter in the bottom, and I got to get rid of that ampere in the top. So that's going to be the units of mu zero times 1 amp over 2 pi times 0.10 meters. So I have to put it in meters, of course. Now you can see this 2 pi down here is going to cancel out with the 4 pi up there and just basically give us 2. So 2 times 1, and this is supposed to be a 1, gives me, in fact, 1 times 10 to the negative 7th. Or excuse me, gives me 2 times 10 to the negative 7th. And then divide it by 1/10. That's the same thing as multiplying by 10. So it's 2 times 10 to the negative 6th Tesla. So at 10 centimeters away, we'd get 2 times 10 to the negative 6. I don't trust my math, not this early in the morning, so I'm going to double check. Let's see, 4 times pi times negative 7 to the negative 7th. And then I divide that by and double check my work. And I get 2 times 10 to the 1, 2, 3, 4, 5, 6. Yes, I was right. Woohoo! I love it when my arithmetic comes together. Now, for part B, we want to know the magnetic field strength at 20 centimeters. Well, I think you can see it's still 4 pi times 10 to the negative 7th. I'll leave off the units this time, times 1 over 2 pi times 0.20. Okay, I think you can see that's going to be half as big. So in fact, you'll end up getting 1 times 10 to the negative 6 Tesla. And then C at 30 centimeters, we're going to get again 4 pi times 10 to the negative 7th, 1 amp, 2 pi, and then 0.30. So it'll be a third of this. So that'd be 2/3, which would be 0.66, which it actually would be 6.67 times 10 to the negative 7th Tesla. Okay. Any questions on that? No questions on that? All right, now what we're going to do is we're going to try to give you an idea of what happens to a current when it's actually in a magnetic field. So, you know, just like a current carrying wire creates a magnetic field, if you take a current carrying wire and stick it in a magnetic field, obviously you can see the individual current carrying wire is basically a bunch of electrons moving this way, or you can picture it as a bunch of positive particles moving this way. Either one works, But we know from the Lorentz force law, F equals QVB, we know that when you have charged particles moving in a magnetic field, they're going to experience a force. So what does that turn out to be? Well, you can use some calculus to actually work out the details, but we don't need that. We just need the result. So it turns out the force, and this is another one of those equations that would normally, we would use this fancy vector equation to get us the direction. So I'm not going to mess with that. What I'm actually going to do is I'm just going to give you the result and say that the magnitude of the force is actually equal to the current times the length of wire in the magnetic field times the magnetic field strength, B. Notice we're using the symbol B for magnetic field, times the sine of the angle between them. Okay. If you're lucky enough to have the magnetic field be, in fact, perpendicular to the direction of the current, then the sine of theta equals 1, and you get this nice, easier expression, F equals Bill, which is my name, so I like that. That makes it funny. Okay. Now, the weird part is, how does this direction actually point? Well, it turns out basically if you point your fingers, your right hand fingers in the direction of the current, okay? So basically my fingers could be any of these directions, including this direction, because these fingers are all still parallel to that. But what I want to do is do it in such a way that my right hand fingers can curl towards the magnetic field. So let's say we had a current carrying wire with the current going upward. So I'll point my fingers this way. But let's say our magnetic field B is this way. If I put my fingers that way on the magnetic field, I can't curl my fingers towards it, right? Nor can I do it that way, right? Nor can I do it that way. In fact, the only way I can do it is turning my hand this way. Then I can curl my fingers that way so that I'm going from what looks like a vector for the current I to the vector for the magnetic field B. And my fingers are doing sort of this number. So that's supposed to be my finger, okay? Does that make sense? Once I have that, then my thumb gives me the answer. So notice when my fingers are curled like that, my thumb is going into the page. So the force on the actual magnetic field, on the actual current carrying wire, is pointing into the board or into the piece of paper here. So again, like I did before, if you draw a circle with a dot in the middle, that's like the tip of an arrow. But if you draw a circle with an X in the middle, that's like the back end of an arrow where the feathers are sticking off. So this force is actually pointing into the board. So this current carrying wire would feel a force pushing it into the page if the magnetic field pointed to the right. So does that make sense to everyone? So it's a weird right-hand rule, and a lot of 202 is about right-hand rules, at least the electricity and magnetism part. Anybody have any questions on that? Okay, so a typical problem might be, let's say we have a magnetic field. Okay, this is the magnetic field. And let's say its strength is, I don't know, let's say 3 Tesla to make it really big, right? And then I have a current carrying wire. Oh, I'll actually draw it this way. With a current going this way. This is totally unrelated to that drawing up there. So we got the wire and the current going that way. Okay. And let's say the length of this chunk of wire right here is only 0.20 meters. So what we have is we have B is equal to 3 Tesla. We have I is equal to, let's say 4 amps. And we have L is equal to 20 centimeters. And finally, we need to know this angle. And in fact, the angle is supposed to be defined basically as the angle between the current carrying wire and this. So let's say that angle is 120 degrees. This is one of those cases where you're pretty much going to stick to the math and only use, you know, I usually use only 0 to 90. So 120 is basically, if I subtract 90 from that, I get 30, right? So you can do something like that. But we need to figure out, one, what is the force? And two, what is the direction of the force? Okay. So according to F equals Bill sine theta, we get F is equal to 3 Tesla, 3 Tesla times 4 amps times 0.20 meters times the sine of 120. I know that got really small there. It says 3 Tesla, 4 amps, 0.20 meters, and sine of 120. Now I'm just going to blindly put that calculator, put that into the calculator, and let's see what happens, and then I'll explain what's going on here. So I'm going to say 3 times 4 times 0.2. Now, obviously, we can do all this math in our head, especially since we know what the sine of 30 is. It's just a matter of changing the sign if possible. In this case, it's not even going to be a change of sign, but I'll say times the sine of 120. Yep, let's say everything. And this would be 2.07. Let's call it 2.08 newtons. Okay. Now, if you work that out, the Tesla is actually, you can only get that sort of from the original mu 0 I over 2 pi r, and then the amp you can work out as well, but ultimately it does turn out to be newtons. That's a good exercise for you guys to try if you'd like, but you're gonna have to use some past information about, for instance, the ampere and the Tesla and all that good stuff. So anyways, the ultimate answer is 2.08. Now, what is the direction? Well, if I lay my hands, again, my right hand fingers in the direction of the current, that would be like that. But I need my fingers to curl towards B through the smaller angle, right? In that case, what we're going to have is QV cross B allows that. And just like last time, it's actually going to go directly into the board or into the page. So it's 2.08 newtons into page. Any questions on that?
Sorry, can you re-explain that last part?
Okay, yeah, that's always the hardest part, by the way, so don't feel too bad. So basically what I'm doing is I'm laying my right hand fingers, and there's other ways you might be able to find, like on Khan Academy and various other websites. They'll show you ways where you can use your fingers like that instead of doing the curly thing. I like the curly thing, but basically you can put your fingers in the direction of I, and then only allow the, notice in the direction of I doesn't give me enough information. My finger can be like this, and that index finger is all still parallel to the current, right? What locks that position down, though, is when I actually turn the, allow my fingers to curl towards where the B vector is. So the B vector is pointing this way. The current vector is pointing this way. So in fact, I get QV cross B, and since my right hand now curls the correct way, where my thumb is pointing is the direction, and you can see my thumb is pointing down. So that's into the page. Did that make sense?
Yeah, that made more sense. Thank you.
Okay. Another way you can do it, just for completeness, in case that way doesn't look that obvious to you, you can basically say this index finger points in the direction of the magnetic field, or excuse me, of the current. Sorry. Let's do that. Let's write an I on there. And I'm going to try to write a B on here. I'm doing this in my left hand, folks, so this is going to look really awesome. And actually, I think I'm giving up on the B. It won't write on my pasty white skin. There you go. Okay. So if you put your index finger in the direction of current, and then your middle finger in the direction of magnetic field, there. Now your thumb is pointing in the direction of force. Okay, so that actually works as well, except in that case I had to bend my finger all the way back to that angle. But yeah, that still works as well. So you can say I is your index finger, B is your magnetic field, then their thumb is the force. Okay, so that's an alternative way if that helps you. If you took pre-calculus or even up through trig, basically what we're doing is something called the cross product. So if you had that in the past, that might be a good thing to go over again to make some sense of these right-hand rules. What I'm going to do right now is I'm going to let you guys go ahead and let's take about a 10-minute break. Let's come back at 10:45. And if anybody has any questions, again, I'm going to be here. I'm going to stop the recording. Unless something comes up that I think the students would find useful, but I'm going to thank you. I almost meant to do that beforehand, and I ended up not doing it and said, I'll just do it afterwards. And yep, thank you. You saved me. I appreciate it. Okay, so we're wanting to make sure give you a couple more examples of how to find the directions of the magnetic fields for a given wire. As well as directions of the force on a charge moving in a particular direction in a magnetic field and stuff like that. So let's start off with the top left. I've labeled each of the wires 1, 2, 3, 4 in the 3 examples. So each of these is a separate example. And this one's another example at the end as well. So what we have is wires put in a square pattern. So they're actually going into the page or out of the page. The red ones are going into the page. The green ones, this one was a mismark, but the green ones are supposed to come out of the page. You can see it's got an X behind it, but I tried to scribble that out by putting a big dot. Anyway, so this is a current coming out of the page, and all the other 3 are going into the page. And what we want to figure out is what is the total magnetic field direction here at this point in the center, okay? So I'll sort of do the first one, and then I want you guys to try the second one on your own, and then I'll do the second one, and then finally I'll let you try the third one on your own, and I'll do the third one as well. So I think you can see that this current carrying wire is carrying current into the page, so I'd actually have to stick my right hand this way around it so that my thumb points into the page. When I do that, I imagine my fingers being like Gumby fingers. I don't know if y'all know who Gumby was, but he was a clay dude. So a clay dude actually has, fingers that'll go concentrically around the wire. So at this point, the magnetic field, let's use blue for the color. The magnetic field due to 1 is this way. Everybody see that? At that point, that's the direction that the current or the magnetic field will be pointing due to that current number 1. So now let's do number 2. Again, the current's going into the wire, so I have to use my right hand like this with my thumb pointing into the page. But in this case, at this point, it's actually pointing this way. So that's the magnetic field due to number 2. And then number 3, again, I got to use my right hand pointing this way, and I see when it gets over here, the magnetic field would be pointing this way due to 3. So you can see that 1 and 3 are actually, since this is the center of the square, and if we're assuming they're all the same currents, then 1 and 3 are actually canceling each other out completely. So far I only have a magnetic field pointing this way, the direction of number 2. But now with number 3, or excuse me, with number 4, that's a current coming out. And at that point, I have a magnetic field pointing this way that's due to number 4. So in fact, the net magnetic field is this way. 1 and 3 canceled out because they're opposite in direction, equal in magnitude. 2 and 4 actually added together perfectly. So I get a magnetic field basically at 45-degree angle if this is in fact a perfect square and all these have the same currents. And that's what we're assuming. They all have the same current. It's a perfect square and this is the center of the perfect square. Okay. Now what I want you to do is try to figure out the direction of the magnetic field for number 1 and draw it and then label it number 1, do it for number 2, do it for number 3, do it for number 4. And then see if you can see what the 4 of those add up to give you. And remember, they're all equal in size, and they're all directions should be basically up to the right, down to the left, or diagonal. So it'd be diagonal to the up and to the left, diagonal up and to the right, diagonal down and to the right, diagonal down and to the left. Those are only directions you can get on this. So y'all go ahead and give it a try, and then I'll work it out verbally and see if y'all come up with the same thing. Okay, I think I've given you enough time. Let's start with number 1. That's a wire whose current's coming out, so I know it goes around counterclockwise. So this side should actually point this way, and that's number 1. I'm going to go ahead and jump to number 3. That one, again, is coming out, so it's counterclockwise, so that should actually point this way, and that's number 3. You can see those 2 cancel out automatically. Number 2, the current's going in, so that's actually clockwise, which means over here the direction would be this way. So that's number 2. And number 4, it's again going clockwise, so the direction will be over here will be this. That's number 4. And I think you can see that the net magnetic field is 0. Okay. Y'all go ahead and try the 3rd example. I'm going to draw it on my own without explaining it, and that should be enough examples for you to feel how to do these type of problems. Okay, hopefully you all were able to get that. Did you get that 1 was pointing down and to the left, 2 was pointing down and to the right, 3 was pointing down and to the left just like 1, and 4 was pointing down and to the right just like 2. Those 4 vectors, of course, are all at 45-degree angles, so they add up to give you a net sum pointing straight down, and that's what that shows. Okay, so now we have another thing to try. Now what we have here is a current carrying loop. So you can imagine maybe the battery was embedded inside of this back part right here. So this is coming out in front of the page and this is going back behind the page. In fact, you can sort of think of it like this. So this part is the front, and this part back here is the back. The current is going this way. Does that make sense to everyone? So the way you can tell which way the magnetic field is at the dead center of that is you actually imagine grabbing this thing with your right hand with the thumb in the direction of current. So in this case, I'd have to grab it like this. Everybody see that? Well, actually, everybody see that? So now my finger in the middle points through in the direction of the magnetic field, and you'd see the magnetic field direction is actually right along the x-axis. So that's a common problem you'll have to be able to do conceptually is if you grab a hula hoop, if you will, imagine it carrying a current in it, you point your thumb in the direction the current's going around the hula hoop, and in the middle, if you cut your Gumby fingers right in the plane of it, the way the blood would squirt out would be basically the direction of the magnetic field at that point. So it should, in fact, be perpendicular to the plane that the hula hoop made. So with this guy, it'd be perpendicular to it. And since that guy is supposed to be oriented parallel to the YZ plane, then it'd have to be in the positive X direction. So when I say X-axis or X direction or Y direction or Z direction, I mean positive. If it was negative, I have to put neg in front of it or a negative sign, okay? So let's imagine some scenarios. What we have here is a charge dead center, because I wanted you to know exactly where the magnetic field is, because this magnetic field's weird. Yes, dead center, it points in the X direction, but as soon as you get off dead center, it points this way and all sorts of crazy stuff. So we're actually just attacking it when it's dead center. So let's imagine a positive charge, and we're using F is equal to QVB, and technically it's QVB sine theta, just like F equals Bill was Bill sine theta. It technically has to be that too. So in case QV is not exactly perpendicular to B, then you have to take the sign between the two. So QV, basically, remember, if you multiply a vector, velocity is a vector, by a scalar, if the scalar is positive, you get exactly the same direction as the original vector. If the scalar is negative, which would mean like a negative charge, then you get the opposite. So QV points in the direction of V if the charge is positive, but in the direction of negative V if the charge is negative. So then we just sort of use that same right-hand rule where this would be QV, this would still be B, and then this would be the force, your thumb, okay? But you got to keep them at right angles like that. So in the case of a positive charge going in the X direction, I think you can see that X direction is in fact parallel to the magnetic field. And of course, the sign of 0 is 0, so you know there's no force here. So I'll put 0 like that. Does everybody follow that? In order for a magnetic field to act on a force that, to act on a charge, the velocity of that charge has to be, at least some component of it has to be perpendicular to the magnetic field. This is a weird thing about magnetism. There's two parts to it. One, a magnetic field will not act on a charge with a velocity v, one, unless it has a velocity, and two, unless that velocity has a component, at least some small component that's perpendicular to the magnetic field. So the magnetic field only acts on things going perpendicularly to it. And then here's the third weird part. The magnetic field always produces a force that's perpendicular to the velocity, the magnetic field. So in other words, you get a force out that's not parallel to the velocity nor the magnetic field. In fact, it's perpendicular to both of those. So it makes this weird little thing, i.e. like this, where you got three mutually perpendicular directions, okay? And the QV that doesn't cause a zero force is only the part that's perpendicular to the magnetic field matters. That's what this whole sine theta does. So now let's imagine the charge being positive so that QV is parallel to QV. That means QV is in the upward direction. So you can say QV is that direction. The magnetic field, however, is in the positive X direction. So I turn my hand over like this, and you see my thumb is pointing into the page now. So that is in fact the negative Z direction. So I'll write this as negative Z direction. So that's the direction of the force if the positive particle is going in the Y direction. Why don't you guys try to take a guess at what the charge going in the positive Z direction, what direction that force would be? I left off a third of my end.
-1.
Professor Younger,
Yes, ma'am.
I'm still a bit confused on the into the page, out of the page concept. Can you explain that?
Okay, so remember we're trying to represent 3 dimensions in 2. So like this diagram right here, X, Y, and Z are all mutually perpendicular. I think you can immediately tell that X and Y are perpendicular, right? Well, in order for us to make it look as if Z is perpendicular to the page, we'd have to draw it at this little weird angle. So sometimes that gets people confused. But in fact, the Z is pointing like that red marker right there, directly perpendicular to the paper. That is the out of the page direction. If I turned it over, that would be the into the page direction. Does that part make sense?
Yes.
Okay, so that one I just did with this version. Let me go back and treat this one right here real quick with the curl way and see if this helps you too. So another way you can come up with this negative Z direction and see if this helps you is you point your fingers of your right hand. You imagine this whole thing is like a hinge, right? This whole, imagine as this is one straight bone and it's the pin and a hinge like you'd see in a door. Well, that thing has to be along QV. In the case of Q being positive, which is all these 3 cases, that means it only has to be along the V velocity, okay? So in this Y direction case, we have the velocity pointing along the Y-axis. So I have to keep my hand this or this. All these different orientations are acceptable. But I need my hand to be able to curl in the direction of the magnetic field. In other words, I need my fingers to be able to curl towards the magnetic field, and they can only do that this direction. So I keep rotating my hand until I find a way that my fingers can curl in the direction of B. Well, B is pointing to the right. So when I get right here, I realize, oh, yeah, that points in the direction of B. So now I see my thumb is pointing straight down when I do that, and that is the negative Z direction. So does that make any more sense?
Yes. Yes, sir.
Okay. All right, so now everybody, since I re-explained that, give the third one a try. So we've got a positive charge, so that means Q and QV are in the same direction. However, the velocity is going to be in the Z direction, meaning coming out of the paper. This way right here. Whee. So tell me which direction the force would be. So this one, I'll clarify, even though I didn't use it over here, I'll say positive Y direction. If you don't put a sign on it, I'm always going to assume that means positive. And if you put something that halfway looks like a sign, I'm going to accuse you of trying to waffle. So one thing you can think about too when you're doing these, as long as the velocity and magnetic field are perpendicular, then the force has to be perpendicular to all three. In this case, I had a magnetic field in the x direction. I had a velocity in a z direction. So the only axis that's left that's perpendicular to, and happens to be perpendicular to both these directions is the y. It's just a matter of figuring out whether it's the positive or the negative y. So that's another thing that can keep you sort of closer to a guess before you actually do the hand thing. Okay. So did everybody get the positive y direction? Anybody not see how I can get it? So these are very critical. These are typical things that you have to be able to solve, and there's an infinity of ways that I can make these up, but they're good fundamental concept questions. Now let's look at the negative charge. So let's say now I have a negative charge in the center. So it might be, for instance, an electron. The magnetic field is still pointing in the positive x direction, but now I have the electron traveling in the x direction as well. Anybody think they know an answer for that? How about this? Does the velocity have any component of its vector? Remember, velocity is a vector quantity. That means it can be broken up into an x component, a y component, and a z component. Does this velocity have any component that is perpendicular to the magnetic field? The magnetic field points in the x-axis, and the velocity points in which direction? In the x direction. So which direction does the velocity point? In the x direction as well. So what should be the force here? It's the one case you can give me a number.
0.
That's right. Because V is parallel to B. Same thing up here. V is parallel to B. So whenever you get parallel, they're automatically going to be 0, period. Which is really different from every other force we're dealing with. Normally things happen only when the force is parallel to the direction you want to go. In this case, it's completely opposite. Now let's try the next one. Again, the magnetic field's pointing in the positive x direction, but the velocity, not QV now, just the velocity is pointing in the positive y direction. So the velocity is this way. What direction is QV? Anybody? Velocity is in the y direction, so what direction should QV be in? Thank you, Kilter, for getting that earlier, by the way. And so Charles too, thank you. And yep. So when the velocity is in the y direction and the particle's charge is in the negative direction, or excuse me, is a negative charge, then a negative number times a scalar gives you a vector pointing in the opposite direction. So QV must in fact be in the negative y direction. So now we're going to do QV is in the negative y direction, so I'm trying to make it point this way, but the magnetic field has to be in the x direction, so it goes like that. So in fact, I end up getting that it is pointing out of the page, which should be the positive z direction. That one's a hard one to bend your arm in the appropriate way. If you try it this way with this thing, QV would point in the negative direction. B would have to be like that. So you'd have to actually look how good I can turn my shoulder. So QV is that way. Magnetic field's this way. You see the thumbs pointing up. I'm still sitting over there, by the way. That's how really flexible my arm is. I'm still sitting way over there. Okay, I'm lying. So you see that the force is in fact in the positive z direction, and you would expect it to be the exact opposite if you got when you had the positive particle, so that's kind of helpful too. All right, you guys try to get the last one. A negative particle moving in the positive z direction with a magnetic field in the x direction. Positive z, by the way, is out of the page, like this. So in this case, we got the velocity is in the z direction, which means the QV is in the negative z direction, which means QV should point into the page like my index finger is doing. I'm shooting the page. Okay? But that's a problem because my middle finger does not point in the direction of B. So let me just stretch my arm. Crack, 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 crack. Okay, I'm lying. That's not really me doing that. So anyways, now my right middle finger is pointing in the B direction, and I see that, in fact, my thumb is now pointing in the negative Y direction, and that's the answer. So the answer is negative Y direction. So again, we see that it's exactly the opposite of what we got when we did a positive charge. So those are really the toughest conceptual questions that you'll get in this 202 course. Normally, 202 courses sometimes cover induction and stuff like that, and there's a lot cooler and more difficult concept questions. But these ones are pretty sweet too. So this will be about as tough as you get in this course, as far as conceptual direction stuff. Any questions on that? By the way, everybody, I do not mind if you unmute and just blurt out the answer. Some of you are typing it. I'm assuming that's because y'all don't have a speaker, and that's fine too. Just want you to know I'm okay with you guys just blurting out an answer when I ask you a question. I don't get offended by anything like that. It's perfectly fine. It's polite. And there's no way ever that you should ever worry about getting an answer wrong. In fact, the vast majority of hypotheses that have made any difference to science have been negative hypotheses, meaning you actually made a hypothesis that turned out to be wrong. So that's the way you learn. So let's kill this. Now, what I'm going to do is imagine a scenario in which we're going to hang a loop of current carrying wire in an actual magnetic field. And what we're going to try to figure out is what is the actual force on the wire, or maybe we'll do it. Yeah, we'll say what's the actual force on the wire due to the magnetic field. So what I'm going to do is imagine a uniform magnetic field pointing into the page. That's what these X's mean. Remember, they're magnetic, they're fields of some sort of origin pointing into the page because they got X's. If they were dots in the center, they would be pointing out of the page. Okay, so what I'm going to do, oh, I thought somebody was talking. So what I'm going to do is imagine a battery up here and then a loop of wire going down. And coming back up so that we have a conventional current I going this way. And of course, it'd be returning back this way. And we're going to basically imagine, or I'm going to give you some currents, and I want you to calculate the force on it due to the magnetic field. So what we're going to do is we're going to imagine the length of this wire from here to here is, let's say, 10 centimeters, 10.0 centimeters. Okay, so I know you can't see that. Hold on, I'm working on it. So the length of the wire from here to here is 10 centimeters. And you might think, well, how long is the wire that's actually in the magnetic field here? So literally there's no magnetic field. It literally ends like right here, okay? Or at least very close to it. So you might think, well, I probably need from F equals Bill, I'll need this length as well. I'll show you that you really don't, okay? I'm gonna say that the current is 125 milliamps is the current. And what I would like to know, already said that L is equal to 10 centimeters. What I'd like to know is what is the force on the wire. and I'll write F sub B, meaning the force due to the magnetic field. Okay, so let me show you how to analyze this problem. So we've got F equals BIL. That's really what we're using. And it's technically F equals B times I times L times the sine of the angle between the magnetic field and the current. You just imagine a little vector that points parallel to the current and you're good to go. Okay. So that's really what you're trying to find the angle between if you put them base to base, the tail of the magnetic field vector to the tail of the current vector, and the angle between them is what that is. So what we first might say is, well, I've got this little piece of wire, and that, of course, is going to give me a force too. So what I have to do is imagine the current vector, which in fact points this way. My right fingers are pointing in the direction of it, right? And the magnetic field, which points into the page. So if I take my right fingers and point them in the direction of current, and then adjust it like this until my fingers can curl towards B, which points into the page, I see that, oh, the force is actually to the right. So the force on this left piece of wire, and we don't know the length, so I can't really calculate it. So we got to hope something works out really great. But the force on the left, which I'll call FBL, okay, for left, I should say, nah, yeah, I'll do big L. Okay, so that's the force due to the magnetic field on the left piece of wire. Now, if I look at the right piece of wire, I see that that the current is going that way. I still need my fingers to be able to curl towards the magnetic field, so I have to turn it that way, and then I see that the force is to the left. So that's the force due to the magnetic field on the right-hand part. So no matter what length they are, it really doesn't matter because this one and this one have the same length. So these two are definitely going to cancel out. They have the same current. They have the same magnetic field strength in it. So these two forces are going to cancel out. That's why I didn't need that length at all. Does that make sense to everyone? Now, I have to deal with this one. So in this case, the current is actually going to the right because it's going around like this. So everybody sees that the current is going to the right down there at the bottom. So if I do current pointing in that direction, that means I can do all this, but I still need to be able to curl my fingers towards B. That can only happen when my hand's in this position. So then the force is actually up on this guy. So that's the force we actually want. It's going to be up. And of course, notice this is actually a perpendicular direction. The L, which is parallel to the current I, is that way. The magnetic field is that way. Those two are perpendicular directions. So this theta is actually equal to 90 degrees. So the sine of 90 degrees is just equal to 1. So I'm left with 0.125 amps times the current, or excuse me, that is the current, times, oh, I forgot to give you the magnetic field, didn't I? Stupid me. Let's say B is actually equal to, let's call this one 3 Tesla. Again, I'm really using really huge magnetic field strengths, just so we can actually get measurable forces. So the magnetic field is going to be 3.0 Tesla. The length is going to be 0.10 meters. Again, you have to use the base units. And of course, it's the sine of 90 degrees, which is, if you remember your sine function, it looks like that. And that 90 is in fact 1. Okay. So what I have is 3 times 0.1, that'd be 0.3 times 1/8. That'd basically be 3/8, which would be 375. And then it's just a matter of figuring out. So this 375 would be 3/8, which would be that times that. And then I divide it by 10. That would be 37.5. Yes, that should be it. I'll double check with my calculator before I commit anything. So I'm gonna say 0.1. I'm using the fact that the 1/8, the fraction, is 0.125. So these first two numbers, when multiplied, is 3/8. That's 0.375. So that would be there. But then I divide it by that, then it should be divided by 10 again. So that'd be 0.0375. So that'd be 3.75 times 10 to the -2 is what I'm thinking. So let's check my math because I'm kind of a goober. Times 0.1. And I get 0.0375, which is 3.75 times 10 to the -2 newtons, which you could also write as 0.0375 newtons. So that's the actual answer. And the point that it lifts up means that when you hang this, say you weighed this circuit with the battery and everything, and you weighed it and it weighed 4 newtons. Let's say weight equals 4.0 newton, 4.000 newtons, just to make sure we have the proper number of sig figs. Okay. Then the apparent weight, when we hung it in this magnetic field, would be 4.000 newtons minus 0.0375 newtons, which I think you can see is 3.9, and then this next one should be 6, and then these last two would be 2.5 newtons. So in fact, it would actually lose weight as a result of hanging it in here, not unlike when you hang a mass in water. The buoyant force, due to Archimedes' principle, actually lifts it up and makes it appear to weigh less. So that's a kind of neat problem. That's a very typical problem as well. I could also work it in such a way that you solve it for the magnetic field. Maybe you figure out what the force on it is. You already knew the weight, and you take this number, work it backwards, and figure out what, in fact, the magnetic field strength is. So that could be used as a way to test the strength of a magnetic field. Does anybody have any questions on that one? Okay. So the fact that this yes.
Shouldn't it be 1 meter in the top equation instead of 0.1 meters?
Oh, okay. So it was 10 centimeters. You might not be able to see it here. That's a cm, and it's 10.0. That was why.
I wrote down 100 on my page. That's my fault. Sorry about that.
No problem. No, and you're probably going to be right about 90% of the time. So always ask that question. That helps me a lot. Like this one, I'm pretty confident this number right here. I can't imagine I was smart enough to pull that off. So who knows? It looks wrong now. Let's try that. 4 minus 0.0375. Hey, I got it right. Who's your daddy? Yep, that's me. All right. So I got that one correct. Now what we want to do is think about some of the things that we can use this for. For instance, people create magnetic fields, and then particles behave in very weird ways. So let me show you an example. Let's say we have an electron. So an electron looks like that. It's got a charge equal to -E, which equals -1.602 times 10 to the -19th coulombs. And let's say it's moving with a velocity v equal to, well, let's use a nice number like 3.0 times 10 to the 5th meters per second. Okay. And let's say it's getting ready to move into a magnetic field that is uniform and points out of the page. Let's say this magnetic field B has a strength of 0.000, that's tenths, hundredths, thousandths. Let's say 10 Tesla. So in other words, it's about the strength of the Earth's magnetic field, on the order of the strength of the Earth's magnetic field. So what's going to happen with this? Well, and we'll imagine this magnetic field's quite long, so it can go a good distance, and it's actually quite big, so it continues on down here. What's actually going to happen? Well, the particle's moving through this way, right? And we know that the Lorentz force tells us F is equal to QVB sine theta. Okay. Well, QV, because the charge is actually negative, QV is actually this way, pointing to the left, in other words. So QV points to the left, B points out of the page. So in fact, this electron is going to feel a force upward. So as soon as it enters that magnetic field, here's a snapshot of it later, where I'm zooming in a little bit. So here's a snapshot of it later. The little electron, which is moving this way, has a velocity this way, in fact, feels a force this way. Okay? Now, if you wait a little bit longer, then the little electron, say, will be going this way because the force has caused it to do that. And now, of course, QV points this way because remember the charge is negative, so it's opposite that. B points this way still. So now you see, lo and behold, the force is again perpendicular to the path. So like that, I think you can see where we're going. The force is always going to be perpendicular to the velocity. So the electron's going to tend to make a loop like this. Does that make sense to everyone? So that's what happens when a charged particle runs into a magnetic field that's running perpendicular to its path, is it starts to spiral around that magnetic field line. In fact, I said spiral. It should actually go in a flat plane in a circle around it, not in a spiral. But if the velocity, instead of being purely in the page, actually the velocity had a little component, say, pointing up like this, then this component right here is parallel to the magnetic field, so that's not going to change at all. That's not going to feel a force at all, because the sine 90 degrees gives you, or excuse me, the sine of, in this case, 0 degrees gives you 0, because the sine function is 0 at 0, right? So the force on that component is going to be 0. So whatever velocity it has, maybe it's going 1 meter per second this direction, that's going to continue going 1 meter per second every second. I mean, for each second that it travels. So the particle is going to do like this with that velocity of 3 times 10 to the 5th meters per second going around in a circle, but it's going to continue to climb at 1 meter per second vertically. So it's going to spiral around this way. If you did the exact same thing with a positive particle, it would spiral around this way. And of course, it would go this way as well if its vertical component was this direction. So it would do the same thing, but instead of spiraling this way, it would spiral the other way. So what I'm going to do is I'm going to calculate what this actual force is and just check it out. And then I'm going to use it to solve something else and figure out maybe I can find out something about the rate at which it goes around that circle. So the force is the question mark we're looking for. It's going to be equal to QVB sine theta. And of course, the sine theta is actually equal to 90 degrees because we're choosing it perpendicular. So I don't even have to deal with that. So it's going to be 1.602 times 10 to the negative 19th, 19th coulombs times 3.0 times 10 to the 5th meters per second times 1 times 10 to the negative 4th Tesla. Okay. So basically what we're going to get is 4.806 times 10 to the negative, so that would be 10 to the negative 18 newtons. That's the actual force, not a very big force, 4.806, and that blue looks horrible on here, so let me write that a little better. So 4.8 times 06 times 10 to the negative 18th newton. That's a really, really small force. But remember, the electron has a mass of 9.109 times 10 to the negative 31st kilograms. So if you assume for a second that G was exactly 10, it would have a weight of 9.109 times 10 to the negative 30 newtons. So 10 to the negative 18 newtons is a buttload of force on an electron. And in fact, that electron is going to spiral in a circle. And what we're going to do is imagine what we can about that circle, or if it actually has a component perpendicular or parallel to the magnetic field, then it's going to make what we call a spiral, or actually it's called a helix technically. Basically, it's going to map out a spring or a slinky shape, okay? And that's what happens when charged particles approach our magnetosphere, basically the magnetic field of the Earth. The magnetic field lines basically take any components of velocity that are perpendicular to them and cause that particle to spiral around that magnetic field, because the other component that happens to be parallel is going to be unaffected. So it'll basically pick particles to spiral one way to the North Pole and the opposite way if they're positively charged, but still to the North Pole, and so on and so forth to the South Pole. That's why we get the aurora borealis and the aurora australis. By the way, boreal comes from borealis, which or borealis comes from boreal, which means north in Latin, and australis actually means south. East, by the way, is orientalis, which is, now you know why they talk about the Orient, which is not appropriate culturally to call people Oriental anymore. And Western is Occidental, if I remember correctly. So that's a totally unrelated sidebar of inane trivia, but anyways, you're here to learn. So now let's imagine that same scenario. Now let's imagine an electron moving in that same magnetic field. And what we're going to do is we're going to picture it actually spiraling around and figure out how rapidly it completes one circle. Okay. If you look, for instance, in your book, you guys are using Giancolli's algebra-based physics. Figure 2018 is a device that we have in our lab and we actually use for our magnetic deflections lab. You'll see pictures of it later, but that is an actual electrons traveling in circles that come as a result of a magnetic field that's set up by those two coils of wire called Helmholtz coils. So now let's attack one of those problems and see what we can find out. So Newton's second law, I always write it like this: the summation of the forces acting on a body of mass m is equal to the body's mass times its acceleration. And notice the vector symbols, because this equation not only gives the magnitudes, it actually gives the directions as well. And in fact, it breaks up into components. Summation forces in the x direction equals mass times acceleration in the x direction. Summation forces in the y direction equals mass times acceleration in the y direction. Summation forces in the z direction is equal to mass times acceleration in the z direction. Okay, there's a reason I'm telling you that now. We also have, I'm going to give you the fancy version of Lorentz force law for just a second. You're not going to be required of it. I just want to show you what it looks like. It's force is equal to QV, and then they use this fancy multiplication symbol, B. That's called the cross product or the vector product of QV and B. But you know, basically the magnitude of the force is equal to QVB sine theta. So what I'm going to do is imagine a electron moving with a velocity v and having a charge negative e into a magnetic field that's big and uniform, but only starts right here. And it goes on forever that way and this way. I'm going to imagine my coordinate system to be X, Y, and actually whenever you draw X, Y, Z coordinate system, it's imperative that the Z be consistent with the right-hand rule like we've been using. So if X points in the direction of my fingers, of my index finger, then Y points in the direction of my middle finger, Z must point in the direction of my thumb, all used with the right hand, or you're going to have bad times when you go to do math. Okay, so Z is coming out of the board, out of the page. So that's the actual orientation I'm going to use. And we say it has a velocity V. It's in a magnetic field of strength B. And what I'm going to do is apply Newton's second law. So the total force acting on this is going to be QVB, because obviously QV is perpendicular to B. Okay. And this is actually going to be the summation of the forces. Oddly enough, it's going to be in the radial direction. So X is right, Y is right, Z is right, all that good stuff. We could use those, but sometimes it's better to use a coordinate system that's radially points inward or something like that. And then you got another one that's perpendicular to that, and then another one that's perpendicular to that. So I can imagine breaking this up instead of X, Y, and Z, breaking up into radial, azimuthal, and Z direction if I wanted to. And then one of the equations would be this one. Okay, so what I'm saying is the QVB is actually going to point perpendicular to the velocity. That's the main thing. So this direction is always perpendicular to the velocity. That's going to equal mass of the electron times the acceleration. Well, if it's going in a circle like we worked out, then that acceleration has to be v squared over the radius of the circle. Remember, A equals v squared over r. That's the centripetal acceleration required to keep something in a circle. So we can actually work out what that radius is quite easily. So this v is going to cancel out with this v over here, and I will get a circle whose radius is given by m sub e, the mass of the electron, times the velocity of the electron, divided by the charge of the electron, and I'm just keeping signs here, so I dropped the negative, I'm just keeping the magnitudes, I said keeping signs, times the magnitude of the electric field. So that's one formula we can use. We actually get that the radius of the circle is mv over qb, which is basically the circle that I was talking about in figure 2018 from your textbook. So that would give me the actual radius of the circle. For the one I did before, it'd be 9.109. I'm going to leave off the unit, times 10 to the negative 31st, times 3.0 times 10 to the 5th meters per second. Oh, I said I was leaving off the unit. Never mind. Over 1.602 times 10 to the negative 19th coulombs. Again, leaving off the unit. Times 1 times 10 to the negative 4th Tesla. Again, leaving off the unit. So if I wanted to work that out, my actual radius of that circle might be quite large. So let's say 9.109 exponent negative 31 times 3 exponent 5 divided by, I'll use parentheses here to keep from making mistakes, 1.602 e negative 19 times 1 e to the negative 4, and say enter. I get 0.017 meters. If you work all that out, it would turn out to be meters. I'll give you some information about the Tesla in a second that'll help you with that. But anyways, all that works out. And basically you get, move the decimal 2 plus decimal places, that give you centimeters. So that's 1.7 centimeters. So the radius would be about that big, maybe a little bit bigger. And the diameter would be about twice as big as that. So any questions on that? Now from that, you could also determine, you say, well, velocity is equal to 2 pi r over the time required to complete one circle, and then you could actually use that to calculate the time to complete one circle. That's called the period of rotation. So that could give you some information. That's a pretty straightforward problem. You could also use that to say, well, how quickly does it go from the page to say 10 centimeters above it? Well, if you you of course actually have to make the velocity have a component perpendicular to the page, which is actually parallel to the magnetic field, and then that would just be a straight velocity problem, no big deal. Velocity or distance equals velocity times time. So those are a lot of different things that you can actually do with this. But all of that gives us some information. Notice how this radius depends on the mass, the velocity, the charge, and the magnetic field strength. Well, if you go into a laboratory, you can pretty much make devices that have what we call velocity selectors. And basically you can set the velocity very tightly so every particle comes out with essentially the same velocity. And then if you have a bunch of particles, some are electrons, some are pions and stuff like that, then the radius is going to be significantly different depending on the mass and the charge. Well, if the pion and the electron have different masses but similar charges, then they would obviously have different rotations. So you can then set up little holes in your experimental device that allow things of one mass to enter here and a thing of another mass to enter here and a thing of another. That's actually called a mass spectrometer, basically. That's a device that, or a mass selector. That's a device that actually allows you to experimentally separate electrons, say from pions or so on and so forth. So that's a very important thing. For instance, if you wanted to make a nuclear weapon, one of the things you have to do is get the right isotope of uranium, and you could do all sorts of things to separate out the different isotopes, but they all have essentially, the same charge but different masses. So you could make a device like this and use that to filter out exactly what isotope you want. So that's some of the things we've used it for in the past. The period, by the way, I already mentioned that to you, so you could actually work that out. Let me show you what that equation is. I already worked this one out for the radius. And in general, the radius for any mass and any charge would be mv over qb. Since velocity is equal to 2 pi times r over the period, you could also use all this and say, well, velocity is equal to 2 pi over the period, and the radius, of course, is m. I know I'm about to run out of page here. The radius, of course, is mv over qb. So now I could actually realize that this velocity is going to cancel out with that velocity. And I could solve for t and get that t is equal to 2 pi m over q times b. And that's an expression that your book has worked out as well. Frequency, which is 1 over the period, of course, is the reciprocal of this, so that'd be qb over 2 pi m. So these are all equations that you could actually use. It turns out when a charged particle goes in accelerates, which is what happens when it's going in a circle, it actually gives off radiation, and this can give you information about that radiation as well. So those are all kind of important principles. The very last bit that we should do is actually talking about the magnetic field, or excuse me, the force between two parallel wires. I've already talked about basically the aurora borealis and the aurora australis and all that good stuff. So what I would like to do is calculate basically the force on a wire due to another wire. So let's start off by imagining two wires with currents in the opposite direction. And this will be the last topic for today. I know you guys will be very excited about this. So let's imagine one wire here has a current I1 pointing up. So current's actually going that way. It's pretending like positive charges are moving that way. And then another wire over here has a current I2 going that way. And let's say the distance between them is D. So I'm going to work this out in terms of pure symbols. I don't have to, I will get an answer that works in all cases as opposed to just the specific case that we were dealing with. So just like this, I'll have a generic answer that works for all cases. These equations are true no matter what, okay? So they're always true. They always be applicable. This one, not so much. This one's only applicable to electron. But by using specific symbols, I get a very appropriate equation that can work for all scenarios. So what I need to do is first think about this. This current carrying wire is going to create a magnetic field. Okay. This one will too, so I could start off with thinking about this one's magnetic field, but it really doesn't matter which one I start with. So I'm just going to arbitrarily start with this one. So this one creates a magnetic field due to charge 1 or due to current 1 at current 2. Okay, so according to the right hand rule, if I grab that wire over here where the wire is, where the other wire is, the magnetic field due to wire 1 will in fact point into the page. So this is the magnetic field due to wire 1 at wire 2. Okay, that's the magnetic field. It points inward, and in fact, its magnitude is equal to mu 0 I1 over 2 pi times d, where d is the separation between them. Do y'all see what I just did there? Does everybody understand why the magnetic field right here, and this is supposed to be lined up with the center of the wire is infinitesimally small compared to the distance d. Does everybody see why that is in fact the magnetic field strength at wire 2? Looks like everybody does. No one's speaking up. Okay, so we now know the magnetic field. Now let's remember that in fact, F equals Bill is applicable here. We have a wire. It's supposed to be, the wire is supposed to be long and straight for F equals Bill to work, and the magnetic field is supposed to be uniform all along the length of that wire for F equals Bill to work. That's actually the more true thing. Long as the orientation of B and L is the same and the strength of B and L is the same everywhere and I, then F equals Bill works. So it even works in a circle as long as the magnetic field is uniform. So F equals Bill is applicable, but as you can tell, the current in this case is this way, and the magnetic field in this case is this way, this way pointing down. So they're perpendicular, so the sine of 90 is going to be 1, so it's just F equals Bill. So this means the force on 2 due to, the force on 2 due to 1 is equal to the magnetic field at 2 due to 1, which actually I changed my orientation with these numbers. I should have wrote this as 2, 1. It depends. Some books and some authors and some people will say it one way and the other way, and others will say it the other way. You could say this is the magnetic field due to 1 at 2, or I could say the magnetic field at 2 as a result of 1. I really should be using that. That's the more common way. So I will call that B21, not B12. So when I do that, the force on 2 due to 1 is the magnitude of the magnetic field on 2 due to 1 times the current I2 times the length of I2, or the length of wire 2. So that's the actual equation, but here's the problem. For this to really be accurate, these wires have to be infinitely long. So that makes it a little bit problematic when you go to actually try to work it out. So what we normally work with is force per unit length, and that works okay as well. So what the result here will be is the force is going to be, and I'm dropping the subscripts now, I'm just going to say it's mu0, I1, I2. See, the I1 came from the magnetic field, the mu0 came from the magnetic field. The I2 comes from the F equation, and all this will be times L2 over 2 pi times D. That is the force that one wire experiences as a result of another wire. Now, the big question is, are these two wires attracted to each other, or do they repel one another? Well, when you go to think about the directions that a force works on a wire, or that a magnetic field applies to a wire, one thing you can do is just imagine the positive charges moving the way that the conventional current says. So let's imagine that positive charges are moving this way because the current is downward. So I have QV downward. The magnetic field is into the board or into the page. So ultimately, QV being this way and B being into the page forces that to be this way. So in fact, these two opposite currents experience a force, or at least this one right here experiences a force this direction. So what we can conclude is that anti-parallel currents repel. So it's the opposite of what charges do. You know, unlike charges attract, unlike currents actually repel. If you work this out again and just said, okay, let's say current's going up, then I have two going this way, then QV would be this way, B would still be into the page, and you'd see that current 2 would be pulling that way. So in fact, parallel currents attract. So those are our big rules. This is the magnitude of it. But typically, like I said, we often calculate the force per unit length because in reality, for this to be fairly accurate, these wires have to make a really sharp angle away from each other. And then that length has to be fairly long and they have to be parallel for a long period of time, or a long distance, I should say. So what we could do is calculate the force. Let's assume for a second that we have two pieces. You could actually imagine this as like speaker wires. Speaker wires and antenna wires used to be two wires that were literally encased in the same sort of housing and ran parallel to each other. So let's say that we had a current I equal to, let's say, 4.0 amps, and that we had two wires that were 4 meters long. So L2 equals L1 equals 4.0 meters long. And let's say they were 3 millimeters apart. 0.003 meters, which equals 3 millimeters. Okay. So they were really close to each other. Remember, a millimeter is sort of about the thickness of a thick toenail. Yeah, that's disgusting. But anyways, let's calculate now the force. So the force, due to these results, due to this calculation we just found, would be 4 pi times 10 to the negative 7th. Again, that's Tesla meters per amp, times I1. Now, what we're going to assume is both these wires are carrying a current I. So I should say I1 equals I2 equals 4.0 amps. So that'd be 4.0 amps times 4.0 amps. And we're going to say they're, of course, obviously anti-parallel because, you know, one wire is carrying the current out and the other wire is carrying the current back. And then I'll divide that by 2 pi times the distance, which would be 0.003 meters, and then times the length, which I said they were 4.0 meters long. So basically what I'm going to get is this 2 pi and this 4 pi cancel out, leaving 2. So I get 2 times 16, that'd be 32, times 4 would be 128. And then 128 times 1,000 would be 128,000 divided by 3. So this is 128,000 newtons divided by 3. But of course, 3 goes into 128, 42.6 times. So 42600 newtons. So that would be a pretty large force. Let's double check my calculations. Oh, I forgot to type it to the -7th. Ooh, times 10 to the -7th times 10 to the -7th. So we ultimately go 1, 2, 3, 4, 5, 6 equals 0.042 or 43 newtons. Now let's check my math just to make sure, because I was doing all that in my head, which is always a bad move. So I'm going to say I got 0.0. Oh, I was off by 1 decimal place. It was 0.00426. And that would be 1, 2, 3, 4, 5, 6. 1, 2, 3. Yeah. So the answer, let me write it, make sure everybody sees what it is. The force would be 0.0042, which I'm rounding to 43 instead of 426. 43 newtons. All right. Any questions on that? All right, so those are the major equations we're using for this material. We're not covering solenoids and electromagnets, magnets, and we're not covering Ampere's law. We're not covering torque on a current loop and applications to motors and galvanometers and ammeters and all that good stuff. However, like I said, you should read this material because it will be in the homeworks in a tutorial way, meaning I don't feel justified in you not having any exposure to it, but I'm willing to only test you on the other stuff. But when you get to the homeworks, there'll be tutorial problems where they tutor you and help you to go through it. I say tutor, it's not physically a person communicating back and forth with you, but they ask you leading questions and you take steps to figure out the answers. So those are counting for you. The other ones that aren't like that, they're just purely extra credit. So, and there's not many of them, by the way, that go beyond section 20.6, which was the last one that I chose to cover. Yeah, 20.6 was the last one I chose to cover. The only last thing I should say to you, remember I earlier mentioned that you should be able to show that the units come out when you do F equals Bill, that the units come out to newtons. So F equals Bill, like that. That's the unit of a Tesla times amp times a meter. The way you can actually do that is remembering that F equals QVB tells you that unit-wise, B, which is the Tesla, is equal to the unit of force divided by charge by velocity. Okay, and that gives you that Tesla is equal to a Newton over a Coulomb for the Newton and the charge, and then a meter for the velocity in a second up here. And I think you can see that the second per Coulomb is equal to 1 over an amp. And then of course, Newton is a unit of force and the meter is a unit of distance. So lo and behold, the Tesla is a Newton per amp meter. So it's a Newton like that. So you can see when this T is multiplied by an amp, that cancels out. When it's multiplied by a meter, that cancels out as well and leaves you Newton. So that was the thing I alluded to earlier about how to actually work out that unit. I didn't technically last time tell you about the unit of the kilowatt hour. I think y'all can figure that out, especially from your reading. But if you don't understand it, let me know. I'll be glad to answer the question during lab or whatever, or just in an email or anything like that. So we're going to go ahead and call it a day for the lecture. I will give you guys a 15-minute break. So come back at 12:15 and we'll get started on our lab. The lab has been posted to module 2. It's actually series and parallel circuits. We're using the same website we did last time. If you guys want to start reading that in this 15 minutes and get started pulling up that page and following instructions, that'll make you finish even easier, even quicker. But I think at the end of the day, the lab today is going to be quite short. So we might even be able to get out quite early. So let's go ahead. I'm going to kill this meeting. We will stop it, and then I will open up the new lab meeting at 12:15. Anybody have any questions before I let you go?
I have a question because
Yes.
I just went to open up the lab and it says there's no content for it. So I don't know if it's like actually uploaded or not.
Okay.
It just
Were you
doesn't-
already opening that module? Because I actually did it during the last one. It had an old version that wasn't good, but you might need to log out of Canvas and then go back in. But I'll check it. Okay.
Okay, thanks.
No problem. All right. See you, folks.